last time that you were looks pretty good. Right.
Nice when technology works.
Okay, let's do a quick sound check. So can people hear me out there?
Yes.
Okay, thanks. All right, so let's begin the review. All right, so this is the second review. So review 2, and this is for midterm number 2. Okay. All right, so let me remind people that the Bulldogs will be going on Wednesday. So if you're a Bulldog in the Bulldog group, you'll be taking the test on Wednesday. And then on Friday, the people who are Georgias will actually go on Friday. Okay. All right, great. All right, so today what we're going to do is we're going to cover 3 topics in the review. So the first topic we're going to cover is the topic on coordinates. Okay. And this involves bases and being able to write out vectors in terms of bases and then sort of picking off the coefficients. And then the next thing we're going to talk about is LDU decomposition. Okay, so remember we can factor, as long as we don't need row exchanges, we can write a matrix in terms of a lower triangular matrix, a diagonal matrix, and one which is in upper echelon form. And then the last topic we're going to cover is determinants. Okay, so let's begin. All right, so what is the idea with coordinates? So first of all, let's let script B be a basis for a subspace. So it consists of vectors v1, v2, up to vt, and let's say be a basis for a subspace W. Okay. Now, we know that every vector can be written as a linear combination side of vectors in B. We also know it's unique because of linear independence. So let V be in W, and V is C1 V1 plus C2 V2 plus CT VT. Okay. And so what I can do is I can write the vector with respect to the basis, and I could just pick off the coefficients, C1, C2, up to CT. Okay, so these are the coordinates of V with respect to the basis script B. Okay. All right, so let me give you an example. We won't do the whole thing, but I just want to illustrate the point of this. So let's say the basis is going to be given by the vectors 1, 2, and 3, 4. Okay, so that'd be a basis. And it's a basis for R2. Okay. And let's say I have a vector V, and it's given by 1, 1. All right. So what I want to do is, on the right, this vector V as a linear combination of elements in B. So I want to write it as C1 of 1, 2 plus C2 of 3, 4. Okay. Now, we've actually seen this before. This turns out to be equivalent to looking at a system of equations. So I can write this out as 1, 2, 3, 4 times C1, C2. Okay, just the matrix equation like that. All right. So this is just a systems of equations problem, and you could just use Gaussian elimination to find C1 and C2. So use Gaussian elimination to solve for C1 and C2. Okay, and then once you do that, you have the coordinates. So this gives vector V with respect to the basis B. Okay, any questions on this? So if I give you a basis for a subspace, I give you a vector, you should be able to write it in terms of coordinates by solving a system of equations. Okay, questions? Okay, so this is a good exercise. You can go home and do this as practice. Finish the problem off. All right, so the next thing I want to cover is the LDU decomposition. Okay, so what's the idea of the LDU decomposition? So let A, B, and M by N matrix. Okay. Sorry. So the point is, let's move this up, try to get rid of that. Okay, here we go. All right, so the point is that we can write A, and then we could move it to upper echelon form, what we call U prime, using Gaussian elimination. So sometimes we actually need row exchanges and sometimes we don't. So if we don't need row exchanges, one can express A as LDU. Okay, so where L is lower triangular, it's a product of elementary matrices. D is diagonal. And then U is in reduced upper echelon form. Okay. All right, so you should be able to do this in practice. So let me give you a matrix. So let's say it's A, and the matrix is given by 1, 1, 1, minus 3, 2, and 2, 1, 0. Okay. So let me kind of go through the process with you. So the idea is we're going to start transforming this matrix. So I'm going to multiply the first row by 1 and add it to the second row and put it in the second row. So that's 1, 1, 1, 0, 4, and 3. And then we keep this row the same, okay? Now, in order to get from the first matrix to the second matrix, I'm applying an elementary matrix E21 on the left of A, and it's just 1, 0, 0, 1, 1, 0, 0, 0, 1. Okay, is that clear? All right. Okay, we just continue on. We multiply this one by -2 now.
Wait, I have a question.
Go ahead.
It's not -3 or, oh wait, never mind, sorry.
We okay? Yeah, I think we're okay. So, all right, let's keep going. So 1, 1, 1, 0, 4, 3. And what do we get next? We get 0, and I get what? -1, and I get a -2. Okay, is everyone okay with that so far? All right, so let's do this. So that's E31, which is 1, 1, 1, 0 here, and then the multiplier is -2 and a 0. Okay, so that's the elementary matrix we multiply by the second matrix to get the third matrix. Okay, so what multiplier do we need next? So what do we need to multiply the second row by?
1/4.
1/4. Okay, so let's do that. So we get 0, 0, and we get 3/4, 3/4, and then minus 8/4, which is -5/4. Okay, and so E32 is going to be 1, 1, 1. Okay, 0. Sorry, there's no 1s here. There's 0s here. And then here's a 0 and a 1/4. Okay. All right, so this is, at the end, this is U prime. Okay, it's not quite U yet because we have to take out the diagonal entries. So then A, well, we need the L part. Well, the L is just obtained by taking the negatives of the multipliers and putting them in the right spot, right? So we have -1, 2, and -1/4. Okay, the diagonal entries come from diagonal entries of U prime, right? So it's 1, 4, -5/4. So that's our D. And now we have to compensate out by dividing all the rows by the multipliers, the diagonal entries in D. So we get 1, 1, 1. What's the next row? Anyone?
0, 1, 3/4.
Good. And then next row after that?
1.
0, 0, what? 1. Good. Okay. All right, any questions on how we did this?
Can you explain how you got U again in that last part?
So I take U prime, right? And I take out the diagonal entries. So the diagonal entries are the ones right here. So I use these as the diagonal entries for D. And then what I'm doing is, remember, I'm taking out D times U and I'm making it equal to U prime. And so in order to get the U, I have to divide the diagonal entries out of each row.
Okay, that makes sense. Thank you.
Okay. All right, other questions? All right, good. So we finished that part off. Now we can go on to determinants. Okay, so that's the third part of the review. Okay. All right, so how does this start? Well, it starts first by you take A to be an m by n matrix. Okay. And we actually define the determinant. So there's a formula for determinant of A via row or column expansion. Okay, so I'm not going to go over this. You should just review it. Okay, so you should know how to do row or column expansion. I think there are plenty of problems that you did in the past on this. Okay, so so that's one way to compute the determinant. So what was it? One of the important facts? An important fact is the matrix A is invertible, i.e., there exists a B such that AB is identity and BA is identity. And this happens if and only if, what's true about the determinant?
It's not 0.
Not 0. Okay, so the determinant gives you a nice way to check whether a matrix is invertible or not. Just compute the determinant. If it's non-zero, it's invertible. If it's equal to 0, it's not invertible. Okay. Now, there are certain ways that we learned how to compute the determinants. Okay, so let me kind of review those methods for you. So the first method was there are formulas for 2 by 2 and 3 by 3 determinants. So I suggest that you sort of know those formulas pretty well. It'll allow you to compute 2 by 2 and 3 by 3 determinants very quickly. Okay, so there's a 2 by, so if I take the determinant of a 2 by 2 matrix, this is AB minus BC. Okay, now with the 3 by 3 matrix, you could sort of go down the diagonals one way, and those give you positive entries, and then you can go down the diagonals in the opposite direction, they give you negative entries. So there's a formula involving 6 terms for like a 3 by 3 matrix. Okay, so you should know those. You should also know how to compute determinants using cofactors and row or column expansion. Okay, so you can take a matrix, you can go along any row or any column, and then you can actually expand using the row entries or the column entries with their cofactors and compute the determinant that way. Okay. So 3, you can use Gaussian elimination . And so there's a nice formula that says the determinant of A is equal to minus 1 to the r times the product of the pivots. And here r equals the number of row exchanges. Okay, so the first condition is if A is invertible. And of course, it's 0 if A is not invertible. If A is not invertible, then one of the pivots is going to be 0. Okay, so you'll be able to tell by using Gaussian elimination whether you can actually invert the matrix or not, and whether the determinant is actually equal to 0 or not equal to 0. Okay, questions on this so far? All right. Now, you also have these. Okay, so these are the sort of 3 computational ways to compute determinants out. All right. Now, what are determinants used for? So let me call this applications of determinants. Okay. So one application is a formula for the inverse of a matrix. Okay, so it turns out that you can write the inverse out using cofactors. So A inverse is equal to 1 over the determinant of A. And then you take the cofactors, but remember, these entries have to be transposed. So C11, C21, Cn1, C12, so forth and so on, C1n, Cnn. Okay? And the cofactor, Cij, is minus 1 to the I plus j times the determinant of the minor, Aij. So remember, Aij is the matrix you obtain by crossing out the ith row and jth column. Okay, so this is the cofactor. All right, so you should know how to compute an inverse that way, right? Now, there's another way to compute an inverse using Gaussian elimination. So if I say on a test to compute an inverse of a matrix, I don't say which way you need to use. You can use either method. You can either use the cofactor method or you can use Gaussian elimination. And then the second thing you should probably review is Cramer's rule. And this involves solving systems of equations. So basically it says the following. So if you take AX equals B, here A is an m by n matrix, and let's say A is invertible, then if I look at the solutions, there's only going to be one solution because of invertibility. So if I look at the solution of this system of equations, then I can write all the entries of the solution just using determinants. So x of I is equal to the determinant of AIB. Okay, so you stick B in the ith column, okay, and then you divide by the determinant of A. So I equals 1, 2 up to n. Okay, so we actually went through this, and for small examples, it's not so bad to compute solutions just using determinants. Okay, any questions on this so far? All right. So the final application I have, and I'll give you a few practice problems after this, is the computation of areas and volumes. Okay. So I'll just draw you a picture. I'm not going to state the entire theorem. So let's say I take two vectors over here, v1 and v2, and I want to know the area of the parallelogram. Okay. So the area of this parallelogram is going to be equal to the determinant of the matrix by just taking vector v1 and v2. And remember, v1 and v2 are in R2. Okay, so they're just, vectors in the plane. And I just put the vectors down the columns of the matrix, and I take its determinant, and I get the area of this parallelogram. Parallelogram. Okay, now, so this is the two-dimensional example here. Now, for 3 dimensions, I could just basically use the same idea. So if I have, sorry, did I get rid of this thing here? No, I didn't want to do that. All right, that's better. Okay, so let me just draw you a 3-dimensional picture here. So let's say I have v1 here, and I have v2 here, and I have another vector here, v3. Okay? All right, so you kind of have to imagine a 3-dimensional object like this, which goes like that, which goes like that, and we have a 3-dimensional object like this. This is called a parallelepiped, okay? So the area of this thing is going to be equal to the determinant of the matrix I do when I put in the 3 entries here, the 3 vectors. Okay? So, and this is the 3-dimensional picture. So the determinant actually has a geometric interpretation. So, in 2 dimensions and 3 dimensions, it's basically the geometric object sort of obtained by looking at the 3 vectors or the 2 vectors, depending on what situation you're in, and computing either the area or the volume generated by these vectors. Okay, any questions on this? All right, so let me give you some practice problems. Okay. So 1. So let A be equal to the matrix 1, 1, 1, minus 1, 3, 2, and 2, 1, 0. So the problem is find A inverse if it exists. All right, so here's a 3x3 matrix. To test invertibility, you may want to check the determinant first. If the determinant's 0, you're done, because then A inverse does not exist. If the determinant is non-zero, then you could either use like cofactors to figure out what the inverse is, sort of using the formula that I gave up here in number 1, or you can actually find the inverse by using Gaussian elimination. Okay, good. And 2, I challenge you to compute the determinant of A, where A is equal to the following matrix. 3, 5, minus 2, 6, 1, 2, minus 1, 1, 2, 4, 1, 5, and 3, 7, 5, 3. Okay? So you can do this either using Gaussian elimination, or you can use the expansion method to do this. Expand along a certain row or column, and then you can reduce it to 3 by 3 matrices, which you kind of know how to compute using a formula. So you can do it that way too. Now, if you need to check your answer, there are programs online where you can plug in the values and check your answer to make sure you have the determinant correct. Okay, there are online programs that compute determinants. You don't have to use Chegg or anything like that. Okay, so this actually completes my review. And so I'd like to open it up to any questions that you have pertaining to the material.
I don't believe we covered transpose in the review, so is it safe to assume it won't be on the test?
Let's see. I think I did. Did I mention transposes? Yeah, I did mention it.
Okay.
Yeah, you should be able to compute a transpose.
Is it 5 questions again?
What?
I don't think you went over it. That's what I was saying before.
You know, you just take the rows and make them the columns, and the columns you make the rows, right? That's all you do to do the transpose. I think you've had problems on your homework on this. Is that correct? Yeah. Okay. Other questions?
Is it 5 questions again?
Yeah. So it'll be 5 questions. Could have various parts because I'm able to give more partial credit that way. Okay, other questions?
Is that just the transpose matrix over the determinant of A? Is that
Sorry.
what ADGA is?
Sorry, I didn't quite understand the question. Can you sort of go over this again, please?
Yeah, for when we were covering finding the inverse of A using cofactors.
Yeah.
So do you just transpose the matrix and then put that over the determinant of A?
Yeah, so let me go back over this. So the cofactor matrix, notice the entries. There's C11, C21 up to Cn1.
Okay.
Okay, so you
Gotcha.
compute the cofactors, but make sure you transpose that matrix if you think of it as C11, C12 up to C1n. Okay.
Oh, okay. So those are C entries. Okay.
Yes.
So those are the cofactors in the matrix.
That's right.
Okay, got it. Thank you.
Okay.
Yeah, I believe you mentioned this last time in the first review, but the applications from the first exam still apply to this exam, right? Like it's fair game.
It's fair game, although, you know, I would know how to do the basic ones, but, you know, it's 5 problems, right? I mean, I'll probably emphasize more on the second part than the first part, but you're still, you know, you're still accountable for knowing the material up until the second, you know, through the 3.3.
Gotcha.
Whenever there needs to be row exchange for the LDU decomposition,
Yeah.
what do you need to do?
So what you do is you sort of do the row exchanges first, and then you look at P times A, or P is a permutation matrix, and then you can write that in terms of LDU.
So would you just, so like LDU would like remain the same, you don't need to do anything special, you just look at PA?
Yeah.
Okay.
Because PA, after you do the row exchanges, you don't need any more row exchanges. So just, you know, pre-multiply A by the row exchanges you need. And then after that, you factor it in terms of LD. All right, so I mean, one thing to think about is we haven't done this too much. So, it's the chances of having to do row exchanges are pretty low, I think. But it's a good question nonetheless on the exam. It is a 50-minute exam. I have to be mindful of, you being able to finish it in a reasonable amount of time. Okay, other questions?
For the initial class, probably gave us seats all the way up.
Yeah.
We just kind of setting it to like 1, 2, 3, 4, C1, C2. We just kind of setting that as the song.
Yeah. Yeah. So here, basically, you can think of it as A times C is equal to V. Well, you can call V equal to D. So this is your B over here. This is your matrix A. It's just a system of equations. Okay. Okay, other questions? Again, the midterm, I just want to kind of lay your fears a little bit, right? I mean, mostly, it's going to be, things that you've seen before. I mean, in terms of computation. So I would really make sure you know how to do the basics like find inverses, ODU decompositions, that sort of thing. Okay. Or there are 5 questions, so I'm going to try to be looking for whether you can actually, perform some of the procedures that we've actually done in the past. So, okay. All right, other questions? No, from you guys? No, everything's good? All right. Other questions from the Zoom participants? All right, great. So we will see you either on Wednesday or Friday. Please try to get here earlier. Again, I'm going to check some IDs and then try to get you situated so we can start the exam on time. I want to really give you the full hour to actually finish the exam. Okay, so see you then.
Thank you.
Welcome.